So, Postscript is kind of a weird language. Not a lot of people tend to be familiar with it beyond, well, everybody knows of it as a page description language. A lot of people have the misconception that it's just a list of graphical elements and that's all there is to it. Nope, it's actually Turing-complete. It is it was, for its time, fairly revolutionary in that, when it was created in, what was it, 1983, or somewhere between 80, or very early 80s. It was not particularly common to see languages that were garbage collected with rich data structures like hash maps and dynamically sized arrays and so on in actual production, much less in embedded platforms like printers. Because it was so early, they squeezed as much of the fancy data structures as they could in, but they didn't realize just how much it also turns out that it can be used as a functional language. Even though it doesn't actually come with any of the combinators that you'd expect, or based on a quick read of the manual, even any way of creating new functions at runtime. So, because of the fact that Postscript is untyped, we have a way of describing stack effect, or instead of describing types, we describe stack effects. And that turns out to be an easier way of dealing with the fact that there isn't really fixedity to functions. And so this is an example of a simple stack effect. It takes two arguments and returns their sum, i.e. the add function. Here's a slightly more complicated one. I don't actually know whether this syntax is standard. It's just kind of what I came up with based on needing it. But this is a function that takes an arbitrary argument, and a function that takes a single argument and returns another value, and then returns that other value. This is more commonly known as the apply function, or in Postscript, exec. Going more complicated still, we have this function, which takes two functions and returns a function that simply applies both of them, i.e. compose. Our last one, our last stack effect takes a single value and a function and partially applies that value to the function, which can be described as running a function that simply drops that value onto the stack and then runs the original function.
What's the plus there?
The plus is functional composition inside curly braces and regular addition outside.
Okay.
This is not typed by, or this is not checked by any sort of tools, and is more of a thinking aid than anything else. And so I figured a little bit of ambiguity wouldn't actually be a problem. So, moving on. Here is a quick guide to Postscript syntax. The most fundamental, or one of the most fundamental types in Postscript is the name. It's roughly equivalent to the Lisp or to a Lisp symbol, and it comes in. There are three different literal representations. The name on its own is called an executable name. You write it, or you type it into the top level. It is executed, and the definition of the name is loaded, and that definition is executed, and that's all there is to it. You can also have literal names, which are preceded by an initial slash, where you type the name and it just leaves the name on the stack, and that's all there is. Finally, there is an immediate name, which we're not actually going to use, but I just mentioned it for completeness. If you have 2 slashes at the beginning of the name, instead of putting the name on the stack, it loads the contents from whatever the global dictionary is and leaves the contents of the name on the stack. Then you have strings, which are enclosed in parentheses, much like in Forth. You have numbers, which behave more or less like I hope that everybody already understands. You have procedures, which are a set of elements that are enclosed in curly braces. And then there are arrays, and there are also arrays and maps. We're not actually going to be making particularly heavy use of arrays, except for, well, actually I lied. This is not the only syntax for arrays. That is another one, which it's not actually no accident that it looks exactly the same as the syntax for a procedure, because a procedure is simply an array with the executable bits set, which implies that if you were to, which implies that these 2 definitions are exactly equivalent, or these 2 lines of code are exactly equivalent. As it turns out, they are. And just to step through this, to step through the second line of code, because we're going to be looking at a lot of code that builds up procedures via code. One thing I forgot to mention, actually, is that every data value in Postscript has an associated executable bit. Most types do the same thing whether the executable bit is set or not. The only exceptions are arrays, which, if the executable bit is unset, just leaves the array on the stack. If the executable bit is set, it interprets it as a procedure. There is also null, which does nothing if the executable bit is set and just returns itself if it's not. And names, which load their definition and execute it if their executable bit is set.
When you say the bit is set, it's a functional setting or it's a mutable setting?
It is a mutable setting. And it is actually attached to the individual data item. So if you have an array and you make a copy on the stack with dupe and then set it to be executable with cvx, you have a literal array on the stack and an executable array.
Okay.
And that turns out to be important. So what we have here is, what we want to end up with is an array that has 2 elements. The first one is the string hello world, and the second is an executable equals. So we start by putting the string hello world onto the stack. We then can't actually create an executable equals directly, so instead we just put a literal down and make it executable. And then we say take the top 2 elements of the stack, put them in a packed array, which is the same thing as a regular array, just slightly faster to run. Make that executable so that it's useful as a procedure, and do some magic to be able, or to run it and be able to look at the actual definition. So it's actually fairly simple to create new functions out of thin air. So Postscript has all of the basic components that it needs to be a good functional language, but they didn't actually go the whole way. It turns out that, Cat, I believe, was one of the first languages that was really combinator-based or functional with combinators, or with higher order functions. The closest that Postscript got is functions like for all, which simply applies a function to each element of an array. There's nothing really that takes a function and returns a function. So, but because we can create our own functions, we can add them. So here's a definition of compose. There are a number of different ways that you could define it with various trade-offs. For a long time, I always defined it by unpacking both procedures and combining them into a single one, which yields something that executes slightly faster, but is also much more memory hungry, and turns out that documents created with that compose function don't usually print.
Why is the exec under dash dash instead of being an exec there?
So, I will get to that in a second. Okay. It is actually a slight bug in the presentation because I changed the definition halfway, this morning when I realized that not every PostScript interpreter defines exec as a primitive, and therefore I needed to define compose slightly differently. You can basically treat it as an artifact of PostScript. So what this does, or the way this compose definition works, is it simply takes the two functions and returns and creates a procedure that sticks the first function on the stack, execs it, and then puts the second function on the stack and execs it. And that has the advantage of being able to share structure over multiple between functions that happen to be composed out of the same parts. I don't know whether I actually need to go through and explain this code. But
yes, please. Okay.
So, the first thing is I need two execs on the stack. So I simply load the exec, or put an exec name in, make it executable, and duplicate it. Then, because of the fact that we don't have particularly much in the way of combinators, I need to use the bare PostScript stack manipulation tools. One the main one of which is called roll. It takes two arguments, a number of items on the stack to rotate, and how far to rotate it. So 3-1 roll takes the top three elements of the stack and shifts the top one of those three to the back of the three. And so you can look at the partial stack effect comment in the middle, which starts with two functions and two execs, and returns the first function, exec, and then the second function, and then an exec. And then after that, I take the top four elements of the stack, which are the contents of the function that I want to run, make a packed array out of them, and make it executable. So fairly simple. The next thing we need is the ability to take elements off the stack and package them so that they can be later put back onto the stack. The easiest way of doing that is just to make a packed array, which you can unpack using a combination of load, which takes all of the elements of an array and just leaves them on the stack, followed by the array itself, and pop, which takes the top element of the stack and removes it, leaving just the contents of the array. However, that's that happens to be inconvenient to work with, usually. It's certainly inconvenient to work with if you expect everything to be a function. And so we simply merge what stash does is it creates that packed array, and then the code to unpack it and packages it all into a function. And because of the fact that it's a concatenative language, packed array can actually take its first argument, or take its argument from the last argument to stash, and that it just works. And you can see via the code at the bottom that yes, it does actually take 3 elements off the stack and puts them in a packed array that will, along with the code to unpack them. Another useful function is const, which is basically the same as oneStash, but it's faster because it turns out that every single implementation of Postscript that I have ever seen is interpreted, and none of the interpreters are very good. And so dispatching to a subfunction, or even dispatching to a primitive, is slow. So what this does is, instead of creating an array and creating a bunch of garbage on the stack, or creating a bunch of garbage on the heap that will need to be considered by the garbage collector, it examines the literal, or the item on the stack itself, and pushes a literal, or the item followed by either the function to turn it into a literal or the function to turn it into an executable as necessary. And this code is, again, fairly simple, but it takes a little bit more time to think through it. And I'm starting to run a little low on time, so I'll skip over actually examining or stepping through it manually. But you can see 2 examples of, yeah, that actually works. So the next function is curry, which I think Cat calls Papply. It is basically a partial application. It just takes one argument, sticks it onto the function.
So what's equal, and how does it relate to the code? Is it?
Okay, so equals, or Postscript has a couple of different print operators.
Okay.
Equals prints strings as just their contents, and everything else as something implementation defined that is usually -- no string val --
So it's print versus write, basically.
Yes.
Okay.
Yes. You'll also see me use the pstack and ppstack, which pstack is the equivalent of applying equals to to just printing every element on the stack. ppstack actually shows the representation of every element on the stack. So yeah, the way that curry works is it simply makes a constant out of the argument, or a constant function out of the argument, and composes it with the original function. A very similar function is keep, which nearly every single time that I have used it, I have followed it by exec, and so I define keep to be the higher order function followed by an immediate exec. But it is exactly the same thing as curry, except for that it pushes its argument after the function has been run. And so you can think of that as hiding the top element of the stack for a moment while you run something else.
I think it's called nip in some.
Nip nip in fourth is actually a function that takes the second or it removes the second element of the stack and leaves the top element. And so it would be equivalent to keeping pop.
Okay, sorry.
And the example adds two numbers while hiding a 1. And of course, no discussion of combinators would be complete without the Y combinator, which is, or if you have seen, there's a usual lambda form of the Y combinator that everybody's familiar with. That's something like lambda f dot lambda x dot f of xx applied to f of xx, which is in fact exactly what this definition is, just written weirdly. Dupe curry is is more commonly known as the U combinator. It applies its argument to itself. And because when this function runs, the top element of the stack is, or before this function has started running, the top element of the stack is the function being run. So we swap that, the U combinator with f and compose it and end up with this function. Further, because we're doing all of the, eta reduction is, I believe, is argument substitution. Because we're doing that manually in the construction of these functions, we can simply apply the U combinator to that again and have the form of the Y combinator that everybody knows and loves. Actually, deriving this is beyond the scope of the talk. Other people have done it far better than I could, or other people have explained it far better than I could, and so I'd recommend that you go to one of those if you don't, or if you need it, if you need that. There's a wide variety of other combinators that you could need. Factor has all of them. But for our purposes, my goal was more to show that just once you have these combinators, you can define functions like the stalwart factorial in a fairly idiomatic functional way, even though that concept had never been, or that concept was never part of Postscript. Or the concepts of creating functions and composing, and higher order functions were never really part of Postscript to begin with. So yeah, key takeaways. Writing Postscript is fun. There's a reason that people like writing point-free Haskell. I keep wanting to call it pointless Haskell, but apparently that gets people irritated. And concatenative languages are basically functional languages where you don't have a choice but to write in a point-free style. Combinators make writing in point-free style much cleaner and more understandable. And yeah, Lisp has the ball of mud property that you can add whatever you want to it, and it will still look idiomatic. You can do the same thing in fourth. You can do the same thing in factor, although you don't need to because they've already done it. So yeah.